So what we've done so far is we've taken an equation given to us in standard or general form, we converted it into factored form, and that is another way that you can see a quadratic equation written. Today what we're doing is looking at the equation in vertex form. So this is the third way that you can see a quadratic equation written. So you can either see it as ax squared plus bx plus c as two factors, or in the form y is equal to a times x minus h quantity squared plus k. So hopefully this looks somewhat familiar. In order to write your equation in vertex form, essentially what we're doing is going through the process of completing the square. So I'm going to go ahead and get started on this. You're given the equation f of x equals 4x squared minus 4x minus 3. And just like what we were doing when we were completing the square, what we're going to do first is group the variable terms together, and we're going to make sure that the leading coefficient is equal to 1, or we're going to factor out the leading coefficient. So we end up getting f of x is equal to, factor out a 4 times x squared minus x, and then minus 3. That constant is just going to stay on the outside. Then to complete the square here, we're going to take half of the b value. Half of negative 1 is negative 1/2. We're going to square it, and this is equal to positive 1 over 4. Again, I can't just add 1/4, or in this case technically 4 times 1/4 to this equation, so I have to go ahead and balance the equation by subtracting 4 times 1/4. 4 times 1/4 is equal to positive 1, so since I added 1 to the equation, I also want to subtract 1 from the equation. Then from here, I end up getting f of x is equal to 4 times x squared minus x plus 1/4. I can factor this to equal x minus 1/2 quantity squared minus 4. And unlike completing the square where we're solving for roots by setting the equation equal to 0, I'm actually going to stop here because this equation now has been converted into what we call vertex form. So again, we didn't do completing the square unnecessarily. I know it's not that fun to do all the time, but the purpose of completing the square is so that we're able to convert our standard form equation into vertex form. You're asked, what are the benefits of a quadratic function when it's in vertex form? Well, hopefully you notice something special about the numbers. I'll give you a minute to look over the vertex form, as well as the standard form, as well as the graph, to see if there's anything special that you notice. Okay, so I'm hoping that in addition to the graph that you already have, as well as the name of this form, was pretty much a giveaway in this case. So whenever you have the equation in vertex form, you actually are always given the vertex of your equation. In this case, the vertex form, the benefits of a quadratic when it's in vertex form is it tells you the vertex. The vertex is always located at the positive h, k value. So we know that standard form tells us the y-intercept, it's the c value. Factored form tells us the roots, which is located as the x-intercept values. The axis of symmetry, we can still use the formula x equals negative b over 2a. And if we convert our equation into vertex form, we now have the vertex of our parabola, and essentially we have the 5 key points in order to graph your entire parabola. What are the disadvantages of vertex form? I don't know if these are necessarily disadvantages, but you don't really know where your y-intercept is located. You don't know where your x-intercept is or your roots unless you set your equation equal to 0 and you actually solve. Again, this is more of a subjective question. Other disadvantages could possibly be that you have to complete the square, so it is a little bit of a longer process, but I'm hoping that as you continue completing the square, you'll actually notice that it's not too difficult to convert your standard form equation into vertex form. Okay, so we will be doing a practice problem together. So what you're asked to do for all of these problems is to change the quadratic function into its vertex form and graph it. And then what you're doing is describing the sequence of transformations that would map k of x equals x squared onto the function given. So before graphing it, what I'm going to do is go through the steps of completing the square in order to write this in vertex form. So a of x is equal to x squared plus 16x plus 71. The first step is to group the variable terms together. Then from here, it looks like the leading coefficient is already equal to 1, so I don't have to factor anything out from the variable terms. I'm just going to go ahead and complete the square. So x squared plus 16x, I'm going to leave a little bit of space, plus 71. Take half of the b value, which is 16 divided by 2 equals 8. Take 8, square it, and then I'm going to add 64 to complete the square. Again, technically I added 1 times 64, so to balance the equation I'm also going to subtract 64 from the equation as well. From here, x squared plus 16x plus 64 is equal to x plus 8 times x plus 8, or x plus 8 quantity squared. 71 minus 64 is equal to positive 7. And now what I've done is converted my standard form equation into vertex form. Okay, so now I'm going to go ahead and graph it. I know my vertex is located at negative 8, comma, positive 7. Okay, and from here, since it's an upward-facing parabola, it's actually never going to cross the x-axis, so there are no real roots in this case. I also noticed that my c value is 71 in my equation, which means that that's where my y-intercept is located, and that's quite far from the points, at least given on my xy axes. This only goes up to 11. So from here, what I can do is graph the rest of my parabola. I can either make a table of values, or using what we know about quadratics and how they have a common second difference, what I can do is, I know that this is my axis of symmetry. So I'm going to graph my axis of symmetry right here through negative 8. And I know that negative 9, comma, positive 8 is going to be another point. Negative 7, comma, 9 is another point. So this is a difference of 1, which means that since the a value is 1, common second difference would be 2. So my next point would be plus 3. So another point that exists would be negative 10, comma, 11, as well as negative 6, comma, 11. You could also make a table of values to figure out these points as well. And once you have your points, you can graph your parabola. And this is essentially what this quadratic function a of x would look like when graphed. What you're asked to do here is to describe now a sequence that would map this function or would map the original function k of x equals x squared onto the function given. So what I'm actually going to do is graph the original function x squared. So my vertex is at 0, 0. Again, it has a common second difference, so that means that 1 unit away from my vertex would be negative 1, 1, and 1, 1. My next one is 3 units away, common second difference of 2. And then the next one is 1, 2, 3, 4, 5 units away on both sides. 1, 2, 3, 4, 5. And then now that I have several points of my parabola, I can sketch this. And this is what my general parabola, or the parent function k of x, will look like. So now I have k of x, I have a of x, and what I'm asked to do is describe the sequence that would map k of x, so map this red parabola onto a of x, the black parabola. So what's special about vertex form is that, let me write out the vertex form. Vertex form is in the form a times x minus h quantity squared plus k. The h value is, again, the x value of your vertex. The k value is the y value of your vertex. It also tells you from the original parent function x squared, h will tell you how many units right or left your function is translated. And again, I'm hoping that this seems a little bit familiar. We did the same type of idea when we were translating an absolute value function. Again, it's the same idea. This h value right here will tell you how many units to the left or to the right your parabola, in this case, is translated. The k value, just like the absolute value functions, will tell you how many units up or how many units down your parabola has been translated. Lastly, the a value in your vertex form will tell you how skinny or how wide your parabola has become in relation to the parent function x squared. If a is positive, that means it's still upward facing. If it's negative, that means that your parabola has been reflected. So in this case, again, the parent function is just x squared. So from here, it looks like to map the red parabola k of x onto a of x, we would have to translate k of x 8 units left, and then we would have to translate k of x 7 units up to map onto a of x. And essentially that's all you're doing when you're describing the sequence of transformations to map the parent function onto our new function a of x. So what you'll essentially be doing for the rest of class is to work on the remaining practice problems. 1, 2, 3, 4, 5, 6 problems, I think, that are still remaining. I'm sorry, there are 5 problems remaining, so you'll do the remaining 5 practice problems, and as you guys are working on it, about every 3 to 5 minutes, I'll make sure that the answers to the next ones are being displayed as well, so that you can be checking your work as you're going along. At the end, fill out that small summary, and if you guys finish before class is done, you guys can access your phones or have the homework assignment posted so that you can get started on your homework as well. It was posted on Canvas as of yesterday, so if you were able to access it and already print it out, you guys can get started on that. Again, if you have any questions, please make sure that you make some notes of it. I'm hoping that this isn't too difficult of a lesson for you guys to follow through, since your quiz did demonstrate to me that you guys really understood how to complete the square. So again, I'll see you guys on Thursday, and have a great rest of your day.